All right, thanks for coming. So I'm going to start the talk out with like a bit of an admission. For most of my programming career, I was completely terrified of C. Like I started out in scripting languages, I did some Java, I've done some Scala, but pretty much every language I've ever used has tracebacks. So when something goes wrong, you know kind of where the wrong thing happened. And I remember sort of like trying to have a go at learning C a few times in my career and giving up pretty early because my programs would fail with like a segmentation fault and no traceback and no information about like what it was even doing at the time that this happened. And for a while that kind of like scared me away. And I just thought, well, I don't really need to use it. I wasn't working on anything performance critical or anything that I felt could really benefit from it. But I kept hearing people I worked with saying about like, big Python projects we were building, like, oh, we can like do most of it in Python and then rewrite the slow parts of it in C. And this was kind of what prompted me to get curious about it because I would hear people say this almost like a throwaway line. People would like repeat this almost as a given. And it sounded really useful, and I knew that, for example, like Mercurial and other pieces of software that I used would have like the diffing and like slow parts of it written in C, and the Python would call out to it, and I was like, I want to learn how to do that for my own things. And I'm going to be showing you today how you can use it for your own things if there's slow parts of your program. CFFI makes it super easy. And so just to do a quick rejoinder of why we would want to call out to C or C++. So the biggest one that's like the most obvious is to make things faster. And generally like string algorithms, diffing, parsing, often some like Unicode operations. If you're like reading through a string that's encoded in UTF-8, there's just really fast C libraries available for doing that. Numeric operations where you don't need the dynamicness of Python. If you're doing an operation over like a large number of numbers, like matrix stuff, that's the reason NumPy is written in C and Fortran. Data structures, if you want to represent trees or like Bloom filters, things that in Python you're going to be using arrays and dictionaries that are dynamically sized. They have like a pretty large runtime overhead. You can kind of do that in C, and it's going to be a lot faster, a bit more memory efficient. Another big reason is access to system libraries. And for example, there's things like syscalls that aren't exposed by the standard library. So sendfile is a really useful one. Sendfile takes a file on your disk and a network socket, like an HTTP connection, and it just sends that file over the network socket without having to copy all the data from disk into memory and then from memory into the socket. I/O things, if you want to talk to like USB devices, SSL and crypto. A lot of crypto libraries you don't want to be implementing in Python yourself. You probably don't really want to be trusting someone else's implementation of them in Python. And then there's like a host of other really useful libraries, C being the lingua franca of computers, like modern computing. C and C++ will often be like the first languages that libraries for a common file format are written in. Things like Thrift and Protobuf are great examples of like the C++ library is almost considered like the reference implementation. I actually know from personal experience, a lot of bioinformatics formats, the reference implementation of a format will be in C++. And then another like not so obvious thing, but actually something really useful, if you're writing a C library, you can write your tests in Python, and this makes it like a lot easier to do sort of generative tests. If you just want to generate like a large number of test cases in Python and do functional tests at the C API level, writing a Python binding and then driving the tests from Python can actually be super useful and make things a lot easier for you. And currently in Python, if you want to interface with C libraries, there's a few existing solutions, and they have their like advantages and disadvantages. ctypes is the one that comes with Python, and that makes it a little bit easier because you don't have to install anything. But with ctypes, you're basically telling it at runtime what to expect in the structs and what function signatures look like in the library that you're interfacing with. And you actually have to link it to that C library at runtime, which can be tricky in a cross-platform environment, and it means you actually have to use libFFI, which basically means every function call that you make, there's a slight runtime overhead, because it has to sort of find that function and do dynamic conversion of different types. So ctypes is a little bit slower and a little bit more verbose. Swig, Cython, and Pyrex are all examples of wrappers where you're going to wrap the C API in some kind of wrapper language, and you'll have bindings generated for you. In all of these cases, there's a little bit more effort if you want it to run on Python 2 and 3, and in some cases, this isn't going to run on PyPy. And then finally, the most low-level way that you could probably do it is you could handwrite a C extension in Python, which is still useful if you're doing really custom stuff. So async I/O, where you really need access to the level, to the interpreter level, or you need to control garbage collection stuff, reference counting. Handwritten C extensions are only going to work for CPython. There's a lot more work that's going to go into it. They're going to be difficult to maintain. They're probably not going to be compatible across major Python versions, like Python 2 and 3. So you've got a few different ways of doing things. CFFI is, I think, slightly more recent than all of these approaches. You don't have to learn or maintain a wrapper language. So basically, all you need is C headers, which is syntax that is pretty simple and familiar, and actually sometimes you can generate this from the source code. The libraries that CFFI generates, the bindings, are compatible with CPython and PyPy, and they're compatible with Python 2 and 3 by default, so that's quite handy. You can avoid the overhead. Remember when I said with C types, there's a slight runtime overhead every time you're calling a function in C. You can avoid that depending on how you set up your project. So there's a lot of benefits to CFFI. And in order to sort of demonstrate how to wrap a simple library, I'm going to go through the example of putting red-black trees in Python. So the idea of red-black trees is set and dictionary in Python are hash table based. And that means you get roughly O of 1 lookups and insertions. But the problem is with hash tables, you can't get fast minimums and maximums. So for example, if you have a set, you might want to know what the minimum element in the set is, or you might want to walk through the items in order, 1, 2, 3, 4, 5. Red-black trees are going to allow you to have relatively fast logarithmic time insertions and lookups, while also allowing in-order traversal and fast minimums and maximums. So also it's a simple enough example for this talk. There's a lot of well-tested implementations out there. So it was kind of a convenient choice. So there are 4 main parts to a CFFI lib. You want to specify, you want to have a setup.py file. And I actually recommend even if you're building this as part of a larger project, writing setuptools files and just having different components to your system in their own Python packages is super helpful. But setup.py is going to make it really easy for you to iterate on the C and iterate on the building stuff separately from maybe the rest of your app. And obviously, if you're writing a library to be published, it's essential. So you need a build file. And basically, this is just going to be a small Python file that tells CFFI what C structs and functions and types to export to make available in Python, and tells it where to find the C code to actually compile. And it's going to sort of tie together your C source code and the CFFI bindings. You'll want the C source code itself, obviously. Although you don't actually need it in every case, but for this example, you're going to want the C source code. And then you want a Python library. So the things you get from CFFI that it's going to wrap for you are just going to be like functions and structs, and it's going to be raw pointers, or like Python objects representing those pointers. And you'll probably want to wrap your C library in a more Pythonic interface. So that's what that's for. I'm going to start with the setup.py. This is like a normal setup.py file, pretty much. There are like two things that are pretty different. So there's this setup requires argument, and what that is, so install requires is pretty familiar. That basically says in order to run and like import this library, these packages need to be available. Setup requires says in order to actually build this package, this needs to be available. And so we need CFFI at the build step as well as at the time of import. Install requires is pretty standard, so you want CFFI in both setup and install requires. And then finally, there's this argument here at the bottom, CFFI modules. And that actually like tells setuptools this project contains like a C module that's being wrapped by CFFI, and here is the build file that's going to do the wrapping and produce the C module for you. So I'll get into that a little bit later, but there's not too many extra things here from a standard setup.py file. So the build file is that file that I mentioned that basically takes like C header definitions and ties them together with CFFI and the C source code and enables the production of this importable like Python wrapped C module. And so we're going to start with the C header. And so you want to create an FFI builder object. So in setup.py, the CFFI modules was a string arbitrary build.py :FFI builder, and that is literally a reference to this variable here. So you create this variable that's imported from CFFI. You define a C header as a string, and basically you can set up structs. You can use most standard C types, including like integer types, like unsigned uint8, like there's a bunch of types provided in the C standard library that enable you to say like unsigned integer, 8-bit, stuff like that. Those are available, strings are available, and you're going to define like basically any function or struct that appears here is going to be available in Python as something that you can call from the library. So it's just going to expose it automatically. Oh, another thing to note is, so I've said here struct arbitrary ... and you can actually use the ellipsis, and what CFFI will do is when it goes to compile this library, it will allow the C compiler to fill in the gaps in terms of like what are the actual fields in that C struct. So that's another thing that's pretty helpful that CFFI does. So we defined that header as a string, and then we need to call ffI-builder.cdef on it, and that just tells it these are the C definitions to use. And finally, there's this little bit here, set source, that defines the module we want to produce, the wrapped like Python importable module. So this string, wait, let me see. So this string here is the name of the module, arbitrary._arbitrary, and we can actually do from arbitrary import under arbitrary, and that is going to be the module that it produces. You put in a string here that is like arbitrary C source code, and then finally you're actually going to provide these arguments, sources and include dirs that tell it like, okay, you need to compile these C files to get all the definitions that you've just specified in the header. And then once you set that up, the final block is just if you run that build file directly, it's going to do ffI-builder.compile. And so that's like kind of helpful for debugging. It's kind of helpful for figuring out if you actually have like compilation issues, like in terms of C itself. The C source file is in that we actually kind of don't need to worry about what's in it. Like, I have found, and I'm going to link at the end of these slides, a nice public domain implementation of red-black trees that uses like a kind of similar API layout to this. But we want that to be just present in the project. And then finally, so once you have that build file written and you have your setup file, you can actually go ahead and run python rbtreebuild.py. You're going to see compiler output. And then finally, when you actually ls the directory of the module that we're trying to build, rbtree, you'll see like an init.py for the module. And it's actually generated this rbtree.so. You know, the file could be named differently on Linux, but it's generated an actual like Python C extension that will be importable. And that's rbtree._rbtree. So, and at this point, you can actually import that. There are two things that are going to be exported from the built module, FFI and lib. FFI is sort of general functions for doing things with pointers and arrays and converting between types. Nothing really specific to a library. The lib object is what's going to actually have all the exported C functions on it. So you can see here we can call like lib.rbtreecreate, lib.rbtreesize. So those were things that I said in my header in the build file I wanted to be exported to Python, and now they're available. And then I'm going to go over quickly how to actually write Python APIs that sort of wrap these low-level C interfaces, because I think that's where like the tricky stuff comes in, because it's actually really easy with CFFI to export like C functions on their own, but it needs a little bit more sort of management to have like a Pythonic API. So there's a sort of typical pattern in C for data structures. You'll have like creation functions that take like some arguments. Often they'll take some like user provided, like an opaque pointer, and they'll build a pointer to like the struct that represents the data structure itself. Functions that operate on that. So for example, here we have something that inserts things in the tree. We have something that finds things in the tree. And then finally at the end, there'll be some kind of deallocation function that takes the tree and like frees up the memory that it was using. A couple of things to note are that the tree creation function takes a callback that actually is going to compare two nodes in the tree. And so I'll talk in a little bit about just doing C callbacks from Python. And there's another callback that's going to handle deletion of nodes. So when we delete a node from our tree in C, we need to be able to let Python know that there's no longer a reference to that object. And so these are the C definitions for those actual callbacks that I mentioned in the previous slide. So the tree comparison function is going to take a reference to the tree itself and two nodes, and in theory it just returns like an integer that says whether one node is less than or greater than the other. And then we have this other like general callback function that takes a tree and a node, maybe like frees up the memory associated with it or does the reference counting thing. So these type defs, which define C like sort of callback signatures, go in your header in the CFFI build file. And then the Python API is actually like relatively simple. On initialization, we call rbtreecreate, and we're going to have some value here that's the comparison callback, and we've actually made a pointer to the rbtree object itself, and just we put that on the tree in C so that we have a reference back to it. So this tree attribute is going to be an FFI like pointer type from Python, and we want to make a set of objects. So basically, when you put an object in the tree, it goes like the reference to that object goes into C, and the Python interpreter no longer knows what's pointing to it. It can't really do garbage collection anymore. because it doesn't have an accurate sense of like whether references to it exist. So we're going to create just like a simple set of the objects that are contained in the tree and keep track of them as we're adding and removing them, so that the Python garbage collector doesn't, we don't end up with a ton of wasted memory. And adding an object to the tree is relatively simple. We can call this function FFI.newHandle, and that gives us like an opaque pointer type that CFFI guarantees you can turn back into the Python object later. We add that handle to the set of objects so that we let the garbage collector know that we're keeping track of it, and then we just call arbitrary insert, and we give it that tree pointer that we made up here, and we give it the handle to that object. And that actually, covers the basis of just adding an object. Remove is also relatively simple. We just create that handle. So we have this Python object coming in. We're going to get a pointer to it. We're going to call lib.arbitrary_remove with some kind of removal callback that's going to free up that memory, and I'll get into that in just a second. The reason I'm doing this like did remove equals not is the C library that I happen to find for red-black trees returns a status of whether the object was actually removed from the tree, and you might want to throw an error or do something else depending on what kind of API you're trying to meet. So if you're doing this for like dictionaries, you do want to throw an error if you delete something that's not present. Set, I think, doesn't throw anything if you remove something that's not present. Oh, and finally, like a really simple one is contain. So we can do is x in the tree. And we just get an object, we get a handle to the object, and we just return is the result of calling this not null, right? So we just, again, this is like an exported function from the library. And FFI.null is like a handy sentinel value that we can use to check for that. So we'll be really quick. We do the callback. So we need a callback for comparing two things. Remember when I did arbitrary create, I passed it this like comparison callback. So there's a few, like there's just a simple thread that runs through your build file and your Python file. In your build file, you're going to say in the header, you're going to say extern Python, and then this function, which we're calling arbitrary node compare. And so this fits the type def that we had earlier of the node comparison function. Extern Python tells CFFI, don't expect to find this in the C source code. This is going to come later from Python. And it's going to be a Python function that I want you to call when the equivalent C function is called. So it actually bounces back out from C to Python. And then in our module, we're going to have this FFI def extern decorator. And we're actually going to define the function. It shares the name of that extern Python function. And this is actually pretty simple. So we just do FFI.fromHandle, and we take the value from the nodes, and we just do a simple comparison. And this is like a pretty standard like C comparison thing. If the first thing is less than the second thing, it returns -1, 0 if they're equal, and 1 if that one is greater than that one. And the helpful thing about this is that standard Python operators are just going to work. So you can just put arbitrary Python objects in, and comparison will work. And then finally, we just pass the lib.exported function. We pass that as the callback into the arbitrary create. So when I previously had like a placeholder for compare callback, we just put that in. And it's a similar one for node removal. So we've got the extern Python here. We're defining it so it's the same name, arbitrary node was removed. And so we just get the tree, we get the value, and we remove the value from the objects. And this is our like node removal callback. And then again, in our remove function, we pass in the lib.reference reference to the same function name. So it threads through the build file, the def extern in Python, and the lib attribute. Oops, sorry. I don't think I have enough time to go over this, but there's like a simple way in the C library that I found to iterate through things in order. And again, so in Python, you are just managing resources, so you have to make sure that you're deallocating things. I know I had to go through that a little bit quickly, but I think that's actually all we have time for, so we're going to go to questions. I'm going to jump to that slide. But I've got some useful links if you want to read more, because obviously it's like pretty reference heavy. And then that link at the bottom is I actually have a Python project that implements red-black trees. It's on GitHub, and you can read that for like sort of the implementation specifics for that.
Well, thank you, Zach. Are there any questions in the audience? Yeah. He was first, and then you can go.
So C++ does like name mangling, which actually makes it like a little bit harder to manage resources. But the way that you normally like export C++ functions to C is with like an extern C section. And that actually will work with CFFI. You just need to sort of explicitly do that because it's a little bit harder to do like the resource management that C++ does. But yeah, if you do an extern C section, you can actually wrap like and call into those like C++ functions. Yeah. Mm-hmm. Sure. So there is a way to basically say, this is the C API, trust me, and I will provide the library dynamically at runtime. I think that it tends to be slightly more dangerous because if you're, for example, distributing a library, you have to trust that the user like has the same version on their machine, or you could have some pretty bad problems. There are like a few different tuning things. There's a thing called FFI.verify, where what you can do is say, here is the API. I don't have the full like compilation unit to like compile all the C source code, but I want you to just verify that the library that is installed and available like matches the API that I'm expecting. And you know, there's a few different ways to like approach this. The one thing is, the thing I said about in your header where you can use literal ... dots and it will let the C compiler fill out the rest, you can't do that if you're allowing the library to be provided at runtime because it doesn't have a compiler available. So.
Any other questions?
Do you expect CFFI to be as fast or faster than the code that's generated by Swig?
So, I would expect it to be roughly the same speed if you're doing this thing where it's actually compiling with the C. There's like a few different factors that go into it. Like what CFFI is actually doing is generating a Python C extension that wraps the C API and that has like a bunch of sort of expectations built in. Because it has the compiler, it can verify certain expectations. But if you're using the more dynamic mode where the library can be provided at runtime, it's going to use libFFI, and that will introduce a runtime overhead. And so I think Swig has a few different ways to actually compile too, and so those are going to like, there's like a combinatorial number of comparisons to make, but I would say you can expect it to probably be like equal to if you're using the thing where you provide the C code itself, yeah. Oh wait, so what is what, sorry? So, as opposed to like, well, the main problem, I mean, if you were just to write your entire program in C, it'd be really fast, probably. So CFFI, I would argue that if there's a library written in C that does what you want, it's always going to be faster to use CFFI, or even any other wrapper for that matter, and call out to C than writing the same thing in pure Python. I would say you can trust CFFI to have like a minimal runtime overhead because at least on CPython, because CPython is written in C itself. And so it's not like, for example, like Java native interface. I don't know if you have any experience with that, where you want to call out to C and C++ code from Java. There can actually be like a huge overhead in that, to the point that sometimes it's easier to just use pure Java, and like faster to use pure Java. I would say that CPython to C, it's almost always going to be like an improvement in performance. So yeah, I wouldn't worry too much about runtime overhead. But there's always like a case for benchmarking, you know, if performance is what you're worried about.
Well, thank you, Zach. If there are any other questions, you can continue talking with Zach outside of the room. Thank you.